Since statistical physics uses probability ideas to describe the outcomes of experiments, we're going to start with a review of some basic probability concepts. First of all, I would like to note that probability is very important for description of many phenomena. For example, we use it constantly in quantum mechanical description of atoms. It is used in genetics, it is used in insurance business, etc. So it is an important topic to study. So it finds applications in many different fields: quantum mechanics, genetics, insurance business, etc. So it's an important topic to study. Okay, so let's start with how we can measure the probability of an event. So if we are going to do a single experiment, for example, if I'm tossing a coin, it is impossible to predict what the outcome of this experiment will be. However, if I form an ensemble of these coins, if I make a set of very large number set of coins that I have similar systems, if I toss all of these coins at the same time, I can basically observe coin 1 gives tail, coin 2 gives head, etc. So I have n of them. So this forms a statistical ensemble, and by counting the number of occurrences of a head in this ensemble, I can say the probability of having a head is the relative frequency of observing the event of getting a head in this ensemble. It's the number of heads divided by the total number of coins. That's basically the definition of probability. All right, so let's note here that it is impossible to predict the outcome of a single experiment So what we do is either we repeat the experiment many times with the same initial conditions. So there are two ways to measure the probability. The first one is the experiment is repeated many times, but then we have to make sure that we have exactly the same initial conditions. Or if we form an ensemble, that's the first important concept in probability, of a very large number I use this funny n. It's theoretically infinite, very large number of similar. Ideally, they should be identical. Similar systems. We can give a statistical description using probabilities. how do I define probability? Okay, so let's say that I have the outcome of the experiment I'm looking at is outcome R. The corresponding probability is PR. The probability of getting an outcome R in an experiment is defined as the number of occurrences of that event, of that outcome, in an ensemble of n similar systems. So this is n is very large, n goes to infinity. So that is the definition of probability. Okay, so PR is probability. So what I have just written here is probability of the occurrence of an outcome R. All right. So basically, as an example, what are these possible outcomes if I'm tossing a coin? So here is 1 Turkish lira. So when you toss this coin, you can get the tail, you can get the head. There's another possibility that it stands on its edge, it's the side, but that probability I'm going to neglect. So it's most of the time either head or tail. So for this experiment, tossing a coin, I have two possible outcomes. Head, I denote this with H, tail, T, and the other outcome, side, neglected. Okay, so that's very rare, so I'm going to neglect this possibility. Now I want to know if I can predict the outcome of this experiment. So using classical mechanics, how would I predict the outcome of this experiment? Well, I need to know the exact mass distribution in this coin. Where is the center of mass? What are the forces acting on this coin as it falls down? The gravitational force, the air drag, etc. So I need to know all the forces acting on it, and I have to do some calculations that could be quite complicated in order to get a definitive answer for where it's going to land when I toss it, if it's going to be, and it's also important how I toss it. So what is the force that I'm applying to toss it? All right, so that's very, very difficult. So I need to use a statistical description in order to predict the outcome of this experiment. So first, as a remark here, I want to note that using classical mechanics, in order to predict the outcome, we need all the forces acting on the coin, and then we need to calculate, we also need to know mass distribution, the location of the center of mass, etc. And plus we would need some enormous amount of calculations in order to predict where it's going to land. Okay, so instead we can form an ensemble of these coins. So here's the ensemble, and we can do this experiment once with all of the coins tossed at the same time under the same conditions. That is, I have a similar system here, so all the coins are similar, so that I'm getting a statistical ensemble, and I do this experiment. Alright, so for one coin I have two possible outcomes. And what are those outcomes? Head and tail. So if I have for two coins, I have head, 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 tail, tail, head, tail, tail. 2 times 2, 4. For capital N coins, I have 2 to the power n possible outcomes. Okay, now if I call P probability of getting ahead, probability of the outcome head, and if I call Q the probability of having a tail, then if I look at the number of, so P is going to be by definition the number of getting heads divided by the total number, and Q is by definition the number of getting tails divided by the total number. And since the number of heads plus the number of tails is the total number, I will see that P plus Q has to be equal to 1. So that's an important result. If I count the probabilities of all possible outcomes, I will find that the total probability should be normalized. So this is called normalization condition. All the probabilities should add up to 1. Okay, now can I predict this probability? Well, if the center of mass of the coin is at its geometrical center, okay, so the center of mass here is right in the okay, I'm having some trouble here. It's right in the middle. Okay, for some reason I can't put a dot in the middle. Anyway, so it's going to be right in the middle, let's say. Then I can predict from symmetry arguments, symmetry arguments, I can predict that P must be equal to Q must be equal to 1 over 2. Okay. Now, in the case of tossing a die, for example, here we have a die. We have 6 possible outcomes. So if I toss a pair of dice, it's going to be 6 to the power 2 outcomes. For n dice, it's going to be 6 to n possible outcomes. So it's going to be analogous to this. So for dice, we have 6 to the power n possible outcomes. So it's analogous to tossing a pair of tossing coin and coins. Okay, so these possible outcomes for dice, what are these possible outcomes? One die is going to give me 1, 2, 3, 4, 5, or 6. So these 6 possibilities. Now, any of these outcomes, getting ahead in the experiment of tossing a coin, or getting 3 in the experiment of tossing a die, these outcomes in the language of statistical description are called events. Okay, so the possible outcomes of an experiment are called events. So, for example, when I'm tossing n coins, let's say, then I'm looking at the event of small n coins are head and n minus n coins are tail. So this is going to be an event in this experiment. In the ensemble where we are trying this experiment, all the systems must have exactly the same initial conditions. So we do this right at the same time so that we are describing this carefully without any changes in the conditions that will affect the probabilities. Another example for events, for example, if I'm looking at this event, people with ages in the range 23 to 24 hospitalized in US. Okay, so that means I'm looking at the total number of people in the ages in the range 23 to 24, and the event is that these some of these will be hospitalized in the US. I can give you another event. Instead of saying people, I can say women with ages in the range 23 to 24 hospitalized in US. So it has to be, so I can say out of all the women in the US, what are the chances that the ages in the range 23 to 24, and then what are the chances that they will be hospitalized. So that would be another event for statistical purposes. Okay, so we have learned two important concepts here. One is the concept of statistical ensemble, the other one is event. So when we are trying to describe a physical phenomena, we refer to probabilistic descriptions frequently. For example, in quantum mechanics, genetics, insurance business, there are many applications of probability. It's an important concept to learn. The probability, another name for it, as we have mentioned before, is relative frequency of an event. So when you do an experiment, for example, tossing a coin, it's impossible to predict the outcome of a single experiment. In order to predict the outcome, you would actually form a statistical ensemble. A statistical ensemble is a set of very large number of systems, similar systems, for which we do the experiment at the same time with the same initial conditions, and we observe the relative frequency of the possible events, and we define the probability of an outcome as the number of occurrences of that event divided by the total number of systems in the ensemble, and theoretically this system number should be very large, almost infinite. And the outcomes that we observe, getting a head, getting a tail, when you're tossing a die, getting a 1, 2, 3, 4, 5, 6, etc., these are all called events. And instead of using the statistical description, it's always possible to try to do this with a classical mechanics or quantum mechanics calculation. Well, in this case, it has to be classical mechanics calculation. You would need to know all the forces acting on the coin, the mass distribution, exact location of center of mass, and if you're doing this for not just one coin but many coins, that would require enormous number of calculations. So for one coin I have two possible outcomes, head or tail. It can also land on its side, but that is very rare, so we neglect that probability. So it's always head or tail. Then if I call the probability of getting a head P and probability of tail Q, these probabilities should always add up to 1, as the number of occurrences of the head plus the number of occurrences of the tail is the total number of systems in the ensemble. So that's called normalization condition. For two possible outcomes for n systems, I would have 2 to n possible number of outcomes for this experiment. For the experiment of tossing a coin, you can say if the center of mass is exactly in the middle, from symmetry arguments there shouldn't be any preference between head or tail, provided that you don't have an asymmetric force acting on this throughout the mass distribution of the coin. So you would have P and Q are 1 over 2. And for dice, we have 6 to the n possible outcomes, because for one die we have 6. For two dice we would have 6 squared, 36 possible outcomes. For example, you can have 1 in the first one, 2 in the second one, 2 in the first one, 5 in the second one, etc. The possible outcomes, as I said, we call events. And example for having an event, if you are tossing, the experiment is tossing n coins, the event could be lowercase letter n coins are heads, the rest are tails, that's an event. More social statistical problem, what are the chances that you will find a person with age in the range 23 to 24 hospitalized in the US? Well, that's an event, so that's people with ages in this range are hospitalized in US. Another event we can talk about is women within the same range of ages hospitalized in the US.